Hi guys, welcome to section 4.8, Newton's method. Newton's method is otherwise known as the Newton-Raphson method. It's similar to our linear approximations, so if you can find a linear approximation, you shouldn't have much of a problem using Newton's method. It's actually how root finders on computers and calculators often work. So first, a reminder on finding an equation of a line tangent to a curve at a point. So if we're given a function f of x and we're looking for the equation of the line tangent at the point x equals a, to find the slope of the line at that point, we find the derivative at a, and then we need the coordinates of the point, so we take a, we stick it into the function, get the output, and then my favorite is point slope form, y minus the y value that you know is equal to the slope times x minus the x value that you know, and then we just clean this up and we get y is equal to, I just add the output here to both sides, f of a plus the slope times x minus a. Now in practice, if we knew the function point, we would clean this up a little bit, combine like terms, and move on. All right, so we're going to now use this to find roots of any function. All right, so what the idea is we're going to approximate the root. So obviously if it was a factorable quadratic or a polynomial, something we could find the exact root, we wouldn't need this method. But let's suppose this is some function, we have no idea what the root is, but we make a guess at the root. So we call that our initial approximation. And I know this is a little far off, but for the purpose of demonstration. So what we do with the Newton's method is we make a guess at the root. We find the equation of the line tangent to the curve. So we're going to find the equation of this line tangent to the curve at this point, right there. And then we're going to identify this point right here, the x-intercept of the equation of the tangent line of our guess. So in general, the equation of the line tangent to the curve at this point is, well, it would be, the slope would be the derivative at our guess, a1 subscript 1, remember subscripts don't mean anything mathematically, it just is saying that was our first or our initial guess, and then the point is a, and then the function evaluated at a, so this output right here would be f of a1, so it would be y equals f of a1 plus the slope at a1 times x minus a1. Now again, what we're interested in is the x-intercept. Where does this line cross the x-axis? Once we find this x-intercept, we're going to find where that point has an output on the curve, and we're going to find the equation of the line tangent to the curve at that point, right here. So that would be a2. We call this our second approximation. So we have an initial guess. We find the equation of the line tangent to the curve at the initial guess. We use the x-intercept of the tangent line as our second approximation. When we find that value, we plug it into the function. We find the equation of the line tangent to the curve at that second approximation. And then we're going to use that intercept. So this would be the third approximation. And we continue on in this fashion over and over again, and we're going to use this point and find the equation of the tangent line. Notice a2 is closer to the actual root right here than a1 is, and then this point, a3, is closer than a2. And that's what our hope is that they zoom in on that point of interest. So what we have to do is to find the x-intercept of this first line. So to find the x-intercept of this first tangent line, the x-intercept is when the output is 0. So we're going to set that equal to 0. We get 0 equals f of a1 plus f prime of a1 x minus a1. And I'm going to solve for x, so I'm going to subtract a1. So f of a, negative f of a1 equals the derivative at a1 times x minus a. 1, whoops, don't forget that, there we go. I'm going to divide out the derivative. So we have negative f of a1 all over f prime of a1 equals x minus a1. Now we're so close, I'm just going to add a to both sides. So a1 plus the function evaluated at a1 all over the derivative at a1 is going to be the x-intercept. So therefore, the x-intercept of the line y equals f of a1 plus f prime of a1 x minus a1 is x is equal to a1 plus f of a1 all over f prime of a1. So that would be this value right here that I put in blue. We're going to use that as our second approximation and repeat the process. Call this x-intercept A2 and use it as our second approximation. And then we're going to repeat the process. With the second approximation. So we repeat the process with the second approximation. So the x-intercept of the second line, so we would just have f of a2 plus f prime of a2, x minus a2. So let me write this down. The tangent line at a2 would be f of a2 plus f prime of a2 times x minus a2, and the x-intercept would be and this line x-intercept would be x is equal to a2 plus f of a2 all over f prime of a2. We'll call this intercept a3, and that will be our third approximation. And then would repeat the process with a3, repeat the process with a4, and then we repeat over and over. And what happens as we do this over and over, our approximations should approach the intercept. So the next approximation is just the previous approximation. Oh, no, I lost something. Oh my goodness, go back. I'm not redoing this. Let's see. Right here, go back to this page right here. Oh my goodness. This is negative right here. This is negative, so this should be negative right here. So the x-intercept is a1 minus f of a1 over f prime of a1. If we continue this would be a2 minus f of a2 over f prime of a2. a3 would be our third approximation. So in general, the next approximation is the previous approximation minus the function at the previous approximation all over the derivative at the previous approximation. So this is the template for Newton's method. And the limit as n goes to infinity of an is equal to r, where r is the root of the original function. So r would be this point right here, where the original function crosses the x-axis. So that's our goal. All right, So, okay, I apologize. All right, so let's use Newton's method, and that is the correct form. It is minus. So let's use Newton's method to approximate the root of the quadratic equation. I know there's other ways to do this. We could just use the quadratic formula, but we're going to show the process because we can only use a quadratic equation if it is a quadratic equation or quadratic function. So this works for any function. So let's use Newton's method to approximate the root in the interval 3 to 5. So we make an initial guess. We could graph this, we could plot a few points to see where this crosses the x-axis. It wouldn't tell us to approximate a root in an interval if the root didn't exist in the interval. So I'm gonna make an initial guess of, I don't know, let's just say 4 because it's in the middle. So my first guess is 4. So I need my function in order to use Newton's method, 2x squared minus 6x minus 5. And I need its derivative, which would be 4x minus 6. Okay. So A1 is 4. My second approximation is going to be my first approximation minus the function evaluated at the first approximation all over the derivative at the first approximation. Right, so now, again, imagine like when we did linear approximations previously, this was a method used by mathematicians to find things like roots and intervals when we didn't have calculators to do this work for us. So we're going to do the math out here, and you should get 4 minus 3/10, right, which is 3.7. Right, so that's a nice approximation. So the first initial approximation we guessed was 4. From 4, they're saying this is a better approximation, 3.7. Now to find the third approximation, we're going to take 3.7 and we're going to pop it into this template. So it's going to be 3.7 minus the function evaluated at 3.7 minus 6 times 3.7 minus 5 all over the derivative evaluated at 3.7. So not sure if you're getting the idea that this is going to get pretty hairy pretty quickly. So this is not a nice number. It doesn't round easy. It doesn't end at the 10th place. So when I pop this into my calculator, I got 3.679545455. Hopefully I did that correctly. Right, so that's my third approximation. So we started with 4. The next approximation was 3.7. Now I'm at 3.679545455. So now I have to take this and stick it into this template right here. So my next approximation, the fourth approximation, well, I don't like writing that number, is going to be A3 minus the function evaluated at A3 all over the derivative at A3. Now you want to carry it out to as many places as your calculator allows for the best approximations or the most accuracy. So you can see right now that this is going to get kind of ugly, lots of room for algebra mistakes. When I do pop this in my calculator, very painstakingly, I get 3.679449474. And then I'm going to take this number and stick it into the template to find the fifth. And I get A5. Oops, A5 is going to be A4. That number minus f of A4 all over f prime of A4. So I'm going to stick 3.679444974 into this right here where I see the thread be this number minus 2 times that number minus, and I'd continue in this process. And if you continue, you get the fifth approximation to be 3.679449472. And you're probably saying, I am not doing that. This is insanely tedious. But what I'd like you to notice that I did do this work. We started with a guess of 4. We went to 3.7. The next one was 3.67, which is pretty close to 3.7. Then when I use this 9-digit number and plugged it into the template, I get almost the same number. I get the same number up to 3 places after the decimal, they match. And then when I use this number to get my 5th approximation, they match all the way up to the 8th number, right? So eventually we're going to keep going and they're going to match it indefinitely. So now here's the key, is how can you get these numbers into your calculator without actually having to pop in these 9-digit numbers all the time? So bear with me. Let's see if I can explain how to do this. All right, so I'm going to go back up here to my original function. And this definitely just takes some practice, but once you do it, your life will be a lot easier. So being able to use your calculator correctly makes all the difference in the world. All right, so I'm going to start with my initial approximation, which was 4, and I'm going to hit enter. All right, so 4 now becomes, anytime I use the answer key, that now becomes the answer into my next equation. So what do I mean by that? Well, here I want to do that 4 that I just have here in my calculator. I want to take 4 and I want to minus 4 plugged into the initial function divided by 4 plugged into the derivative. But instead of using 4, I'm going to use the answer key, and I'll explain why in a minute. So if you look above the minus sign on your calculator, you have above the negative sign, it says answer. So I'm going to do second answer minus, now we have a fraction here, so it's essential that you put the whole numerator and the whole denominator in parentheses. So I'm going to emphasize that right here. All right, we're going to do that. And I'm going to do parenthesis. I'm going to do 2 times. Now I'm using the 4, but I don't want to use 4. I'm going to use the answer, thus taking that 4, and then I'm going to square it. So 2 times answer squared minus 6 times answer minus 5. I'm going to close the parentheses because that's my whole numerator, and divide it by my whole denominator, which is 4 times the answer minus 6. All right, and I'm just going to hit enter, and that comes up to be 3.7. Now what's really super cool about this is if you look above your enter button, what does it say? I can't read it. It says entry. I believe that's what it says. Mine is blue and faded. So if I hit second enter, it's literally going to retype what I did previously, but now instead of using the 4, it's going to use the previous answer. So it's going to do this calculation. It's going to do 3.7 minus 2 times 3.7, so forth and so on. And when I hit enter here, that's how I got the 3.679545455. So that was my third approximation. So now I'm going to take this number and stick it into this template. I hit second enter. It's going to do the previous answer minus the function evaluated the previous answer divided by the derivative at the previous answer. And I get 3.679449474. I hit second enter again. It's going to take that answer and give me the next one. And that's how I got the 5th iteration. Now notice when I do it again, I get my 6th iteration. It's exactly the same as the 5th one. So I know from this point forward, that's all my calculator is going to give me. And I'm going to use this as my answer, because A6 is A5 minus the function evaluated at A5 all over the derivative at A5. And I get the same approximation. So it must be accurate out to at least 9 places or more. And just follow the directions in the book. So that root, where that function, this crosses the x-axis, is 3.679449472. All right, so let's try another one. Let's use Newton's method to find the root of this 4th degree polynomial. So again, we could use the quadratic formula for the previous one, but I was just trying to show you the process. So here we don't have a template to find roots of 4th degree polynomials. So we're going to make an initial guess. You can lean towards one side or the other. You could graph this if you wanted to, but it's sort of defeating the purpose. I guess using our calculator period is defeating the purpose. So I'm going to say, let's assume my first approximation is 1.5. So my second approximation, according, well, actually, let's write this. F of x, my derivative, my function is 3x to the 4th minus 5x squared minus 6x minus 5. My first derivative is 12x cubed minus 10x minus 6. So my second approximation is going to be my first approximation plus, minus, goodness, don't make that mistake, minus the function evaluated at the first approximation all over the derivative evaluated at the first approximation. So I'm going to do this right in my calculator from the get-go. I'm going to clear it. I'm going to do 1.5. I'm going to hit enter. So that's now my answer. And I'm going to now do that answer. Let me slide this up. All right, I'm going to do that answer minus the function evaluate the answer. Make sure you put the whole thing in parentheses. So it's going to be 3 second answer to the fourth. Whoops, nope, don't do that. Answer minus parenthesis 3 answer to the fourth power minus 5 answers squared minus 6 times the answer minus 5 divided by whole thing in parentheses, the derivative 12 answer cubed minus 10 times the answer minus 6. All right, let's see. So the second approximation, we guessed that it's a halfway between 1 and 2 is 1.5. We plug 1.5 into Newton's method, and we get something a little outside of the interval, which is okay because we're not too far out. 2.016025641. So now I'm going to use this. Now I don't even have to type that all in again. Once this is in your calculator and you hit, sorry, I'm trying to get rid of that glare for you. There we go. I hit second enter. It's as long as you did that correctly, you just hit enter and it's going to pop 2.1062, that whole long number in there. And I get my third approximation is 1.8478147882. Let's do approximately equal to. And then I'm going to repeat the process. I'm just going to do second enter, and I get 1.81237247. Second enter, enter. And I'm going to start seeing some consistency in these numbers. They're going to start looking more and more like 266. I'm going to hit enter again. A6. I'm getting there. 1.81089176. I hit enter again. Oh, and now I'm at A7. I get the same thing. So that's where I can stop. So I can determine that the root of this original function that falls between 1 and 2 is approximately 1.81089176. Okay. Using Newton's method to approximate radicals. So we're going to use Newton's method to approximate the cube root of 50. What number times itself is equal to 50? Again, fortunately, we have calculators that will do this work for us, but back pre-calculator days, they needed other methods to do this, so this is how we would do this using calculus. So to approximate the cube root of 50, this is equivalent to solving the equation x is equal to the cube root of 50, because the cube root of 50 is this. It's just, we just set it up. We want to solve for x. But now I'm going to undo the cube. I'm going to cube both sides. So x equals the cube root of 50 is equivalent to solving what number cubed equals 50. But we can turn this into a root finding problem by setting it equal to 0. This is equivalent to solving x cubed minus 50 equals 0. So if we call this our function f of x, we're really just doing a root finding problem. So we're going to let f of x equal x cubed minus 50, and we're going to use Newton's method to solve this. Then the derivative would be 3x squared. We have to make an initial guess. So we need an initial guess to solve the root of this problem. So we have to initial guess. Okay, if your initial guess is far off, weird things can happen in Newton's method. It can go all off kilter and we can experience what we call chaos. So we want to get a number that makes most sense to us. Notice 3 cubed is equal to 27 and 4 cubed is equal to 64. So therefore, the number we're looking for, what number cubed gives us 50, must fall between 3 and 4. So A1 must be in here. Or A, what we're looking for. So pick a number between 3 and 4. Let's let A1 be right in the middle, 3.5. All right, so we have our functions, and we have our initial guess. So now we're going to use our template. And this is all stuff you could do without a calculator, but we don't do it. We're just trying to understand the process. So then A2 is going to be A1 minus the function evaluated at A1 all over the derivative at A1. So I'm going to use my calculator because I have the technology to do it. I'm just trying to understand the process. I'm going to clear it. My initial guess was 3.5. And I'm going to do second answer minus the original function, which is x cubed minus 50 in the numerator. So I'm going to do second answer cubed minus 50 in the numerator divided by the derivative, which was 3 second answer squared in the denominator. I hit enter, and I get 3.69. So I'm going to write out that approximation, and I'm going to write all the digits that my calculator gives me. It's 3.693877551. So my third approximation is we're going to stick this back into the template, or we're going to let the calculator do the work for us. I hit second enter. Now it's going to take this previous answer, or my second iterate, and it's going to give me 3.68. So we see we're getting closer. 3.68, 405772. My fourth iterate. I'm going to do second enter and hit enter. And we can see that the numbers are going to be getting more and more similar. 40. So we're accurate out to 4 places right now. 31499, because they match up to the previous answer up to 4 places. And we want to keep going till our numbers are identical as far as our calculator gives them to us. Oh, and there we go. We're repeating A5 is the same as A4. So that didn't take very long. So therefore, the cube root of 50 is about equal to 3.68403149. And I'm going to check. I'm going to do math. I'm going to do the cube root of 50 and see that we get the same answer. So why do we do this? Again, we're just trying to understand calculus and the processes that led us to all these big and great things that we're learning. To do in your text, read 4.8 in your textbook, which is Stewart. Exercises 7 to 15 odd and 23. And then you're going to do corresponding X, Y, Z homework. So you need to check your, let's see, do I have it here? 254, Newton's method 4.9. I think this might be the same section. Not 100% sure, but check on Blackboard because I give you that little grid that matches this up. And keep posted for, is this 4.8? This might be, yep, I think this is 4.9 in Stewart. Again, I mean in XYZ. Again, go to Blackboard, see Blackboard for the corresponding. I give you each the Stewart section number and then the XYZ homework number. So make sure you see your to-dos in Blackboard. All right, catch up with you guys shortly. Bye-bye.